Next question comes, how do you assign electrons to atoms? Like, do they go in random or is there an order? Well, there's absolutely an order, all right? Back in the days of Bohr, which we talked about in Chapter 6, Part 1, Bohr saw that the energy of the different places where electrons go is basically has just an n dependence. He saw that energy equals minus RHC times 1 over n squared. H is Planck's constant, c is the speed of light, R is the Rydberg constant, which you don't have to know / memorize, but it is a constant. So on all of those, the energy really just has an n dependence, and that worked great for hydrogen and the helium plus 1 ion. But when you have more than one electron, Bohr's rule doesn't work very well. And it's basically safe to say that when you have more than one electron, the energy depends not on just n, but on n and l. So the so-called n plus l rule is just the fancy version of what Bohr did. And instead of having just an n dependence, there's actually an n plus l dependence. So we're going to be using a lot the SPDF letters, and using those letters to find the L rule. If we add the L to the n value, the lower n plus L will be filled in first, and the higher n plus L will be filled in last. The picture on the left there shows what happens when you have like just a hydrogen atom. And because in a single electron atom, the energy depends just on n, you can see that 1s would be filled in first, and then 2s and 2p would be filled in essentially at the same time. There's no preference. And all the 3s would be after that, and the 4s and stuff like that. But once you have more than one electron, that's when you need the n plus l rule. And the n plus L rule is pretty important, all right, because this is what scientists, what chemists use to tell the order of electrons in an atom. And you can actually go through and figure out the n plus L values and go from lowest to highest, or there's other ways to do it we'll talk about here in a little bit. But in current theory, the n plus L rule works really well for assigning electrons to atoms. If you do have two values of n plus L that are the same, and we'll see examples of this. All right, so for example, 4s and 3p are going to have the same n plus L value. The lower n is filled in first, and the higher n would be filled in last. So 3p would be filled in before 4s, and we'll see this here in a little bit. This is kind of a cool video.
In a single electron atom, hydrogen, subshell energies depend only on the subshell's principal quantum numbers. In a mini-electron atom, the presence of electrons in one subshell affects the energy of other subshells. Consequently, the subshells are not filled simply on the basis of the principal quantum number.
The n plus L rule assumes what's called zero-point energy, which is the lowest energy state possible for an atom. Most of the time in the real world, because of like energy from the sun or nuclear radiation or any kind of reason, sometimes you have excited states, but we're going to assume that everything is behaving itself basically and pretty chill. So we're going to talk about then how we can predict the default energy system for the different atoms. And it works out pretty well. This is called an Aufbau diagram that we're looking at right here. Aufbau comes from a German word which means building up. And supposedly Bohr and Pauli in the 20s and stuff started figuring this out. There's different ways to write Aufbau, and you can do it any way you want. But what you want to do, I'll make like a cheesy one here. You start off with 1s, 2s, 3s, 4s, etc., etc. Then you skip one and go up to the right, and you start with the p's, so 2p, 3p, 4p. Then you skip one, go up to the right, 3d, 4d, and then the next one would be 4f. And you can keep going higher, but notice these arrows that go through it, all right? Those arrows are the configurations that you'd fill in the electrons. So this diagram obviously is better than my cheesy diagram. Here's the n plus L equals 1. Now, for 1s, remember, L equals 0, so 1 plus 0 equals 1. 1s is always going to be the orbital filled in first. And n plus L would be 2. 2 plus L equals 0 for S would be N plus L equals 2. That's the next one to get filled in. Now, both 2p and 3s have the same N plus L. If you figure it out, they're both equal to 3. Lower N filled in before higher N, so 2p gets filled in first, and then 3s. The next group there is what we talked about earlier. There's 3p and 4s. They're both N plus L equals 4. Lower N before higher N, 3p before 4s. Now notice though that 4s in the fifth arrow there, if you will, does get filled in before 3d, and that's kind of interesting at first, but this is a result of the N plus L rule. Now, why this is important is that those arrows literally show how you fill in electrons. You're always going to fill in the 1s first, and the 2s will follow, then 2p and 3s, and 3p and 4s, etc., etc. And that's really, really cool. You can use N plus L numbers to figure that out, or you can just follow the Aufbau diagram, and either way is fine. But obviously, when you're putting electrons in systems, this is where it is. Now, again, if you've dealt with these kind of things before in the past in other chemistry courses, you might remember that, for example, carbon is 1s2, 2s2, 2p2. Cool. Carbon is 1s2, 2s2, 2p2 because there are 6 electrons. The s orbitals, as we saw earlier, always hold 2 electrons. P's can hold up to 6. So if you have 6 electrons total, the s's hold 2, so 1s2, 2s2, and then 2p's hold up to 6. Carbon has only 2 more electrons to go, so that's why it's 2p2. Hopefully it's starting to come into focus a little bit. But again, the goal is we're going to have very exact energy diagrams for how the electrons are placed around atoms. This is going to be the next step, is how do you write atomic electron configurations? And earlier I said for carbon, 1s2, 2s2, 2p2. If that's Greek to you right now, please don't worry about it. What I'm referring to here is what's called spectroscopic notation, sometimes called SPDF. And we've seen here, for example, the NL notation. So on the lower right corner there, it says 1s1. Again, the number is the N that starts it off. The letter corresponds to L. S means L equals 0, P means L equals 1, etc. And the new thing now is the number of electrons, which is given as superscript. So 1s1 would be the electron configuration for hydrogen. Hydrogen has 1 electron. Remember, the 1 on the periodic table means 1 proton. That's the atomic number. But in a neutral atom, 1 proton would have 1 electron. So neutral hydrogen atoms would be 1s1. If you want to go one more to a 1s2, no problem at all. 1s2 would be the electron configuration for helium. Now, helium has 2 electrons total. 1s's can have up to 2 electrons. So 1s2 would be the SPDF or spectroscopic notation. Now, sometimes you're going to see these listed in what's called orbital box notation. This orbital box there with a 1s and a square and an up and a down arrow, and don't worry about the color coordination. But anyway, that's another way to write 1s2. And notice the up and the down. Those correspond to the positive 1/2 and negative 1/2 values for m sub s. Spin is basically how electrons spin around, either clockwise or counterclockwise. Pretty cool. So 1s2 would be the spectroscopic notation way of saying what the electron configuration is for helium. On the other hand, you could have an orbital box notation. You'd have literally a box with a 1s under it and 2 electrons. Sometimes I will just write the line under it, and I'll write arrows that look pretty cheesy, something like that, but they're all the same thing. There's going to be a reason why orbital box notation is pretty handy. This is kind of the overall view of how electrons get placed in. And in chemistry, like all the physical science, all right, it's always about the energy. So on the left-hand side, it says order of filling. That's really the energy distributions here, how we go. 1s is always the first in, 2s is next, 2p, 3s, 3p, 4s again before the 3d like we talked about earlier, but then 4p, 5s, etc., etc. We're going to use these to figure out the atomic electron configurations of atoms. One thing that's going to be somewhat helpful to us eventually too is to know where the blocks are on the periodic table. Now remembering that s orbitals can only hold 2 electrons and p orbitals can hold 6 and d's can hold 10 and f can hold 14. The left 2 columns, which for this discussion also includes helium by the way, those are called the s block elements. So 1s2, like we saw hydrogen was 1s1 and helium was 1s2, they're filling in, those are the outer electrons of that system. So they call that the 1s region. 2s is under it, and we're going to see 3s is there. The right hand 6 columns, starting with boron and working over to neon and basically going down, those are called the p block elements. So s is on the left, P's on the right. We're going to see the D's are in the middle, and the F's are the lanthanides and actinides at the very bottom. So the actual order, the way the periodic table is configured, has a result of the electron configurations, which is kind of interesting too.